All right, greetings everyone. Welcome to the second part of the video for section 7.1. In the first part, we talked about different methods of solving quadratic equations. Now we're going to use those techniques to help us to solve some trig equations. So let's take a look at some examples here. So we're asked to use our information from before to help us to solve each of these equations given below over the interval 0 to 2 pi. And notice the way that interval is written. It does include 0, but not 2 pi, so we want to answer 0 to 2 pi, not including 2 pi. All right, so on the first one here, we have 2 cosine squared t plus cosine of t equals 0. And what we're going to do to start here is we're going to use a u substitution like we've used in chapter 6. However, in this case, instead of having u be something that's inside of a trig function, we're actually going to have it be a trig function itself. So I'm going to have u equal cosine of t in this case. And then when I do that, I can replace everywhere where I see a cosine of t in this equation with u. So this will become now 2 times, since it's cosine squared, this will now be u squared plus u equals 0. And when you see this, hopefully you recognize that it looks very similar to the equation we had, which was 2x squared plus x equals 0 from the previous video. And recall when we solved this one, we ended up with the answers x equals 0 and x equals -1/2 by factoring out the x. So as you can imagine, in this equation up here, we will have u equals 0 and -1/2. Okay, so this is how this connects. Over here, we're not solving for the value of u, right? We're trying to find the values of t. And notice above, again, we have this equality that u equals cosine of t. So we can now rewrite these equations as now instead of u equals 0 and -1/2, we can have cosine of t equals 0 and cosine of t equals -1/2. And then these we know how to solve from chapter 6. So cosine of t equals 0. We're just thinking about where on the unit circle this cosine equals 0. And there are 2 such places at pi over 2 and 3 pi over 2. And then where cosine of t equals -1/2, we're thinking about the 2 places where cosine equals -1/2. So we know we'll be in the second and the third quadrants. So we'll be looking at 2 pi over 3 and 4 pi over 3. Okay, and those would be our answers there. Isn't that great? Isn't that fun? Yeah, I agree. All right, let's look at the next one. So here we have secant squared of theta minus 5 secant of theta equals 6. And here I'm going to again start by replacing my trig function with the variables. So I'm going to say that u equals secant of theta, which then means we can rewrite this as u squared minus 5u equals 6. Which we see this as a quadratic, so we can subtract 6 from both sides. We want to make this equal to 0. So when we do that, we end up with u squared minus 5u minus 6 equals 0. Which again, comparing this to what we've done before, this looks like kind of like the one x squared minus 5x minus 6 equals 0 that we solved before. And if you recall, the way we did that, excuse me, was by factoring. So this can be factored to u minus 6 times u plus 1 equals 0, which then gives us u equals 6 and u equals -1, which is what we had before. Now, we're not looking for the values of u, we're looking for the values of theta, right? And we have again up here that u equals secant of theta. So we can make that substitution. So we have secant of theta equals positive 6, and secant of theta equals negative 1. And in our unit circle, both on our unit circle and in our calculators, we don't have secant buttons, but what we do have are cosine buttons. So rewrite each of these in terms of cosine. So this first one, secant of theta equals 6, we can rewrite as 1 over cosine of theta equals 6. The second one here as 1 over cosine of theta equals negative 1. But we can't really solve these again because the cosines now are in the denominator. But we've seen a problem like this before, and I'm sorry, move this up here. Okay, so the way we deal with this is we just reverse both sides, which again is legal if we do it to both sides at the same time. So for example, on this first one where it's 1 over cosine equals 6, I'll make the 6 as 6 over 1. I'll flip the left side so it becomes cosine of theta over 1, or just cosine of theta. And the 6 over 1 will become 1/6. And then we do the same with the right-hand one. So 1 over cosine of theta just becomes cosine of theta over 1, or just cosine of theta. And then negative 1, we can make negative 1 over 1, but when we flip that over, it's still 1 over negative 1, which is the same as negative 1. And then again, from chapter 6, we know how to solve these. So cosine of theta equals 1/6. We have to use our calculators and inverse cosine. For that one, I'm not going to go over all the details of that, but when we do, I believe we end up with theta equals 1.4033 and 4.8798. And then for the second one, cosine of theta equals negative 1 was only one place where that happens on the unit circle, and that is at an answer of pi. So for this one, we get that our answers are theta equals 1.4033, 4.8798, and pi. All right. Sweet. Let's move on. All right, our first one here now, we have 2 sine squared t minus 1 equals 0. And you're probably catching on by now. We'll again start by doing a u substitution. In this case, I'll make u equal to sine of t. This becomes 2, oh my lord, come on, Cody. This becomes 2u squared minus 1 equals 0, which again, hopefully you recognize that this is similar to the problem we solved that was 2x squared minus 1 equals 0. So for the one with u, we would just isolate the u by adding 1 divided by 2, taking a square root on both sides. And we do that, we'll end up with u equals plus or minus square root of 2 over 2. Again, we did this in the previous video. And then as before, or the last few ones, we are not trying to solve for u, we're trying to solve for t. We know u equals sine of t, so we can rewrite these as sine of t equals positive root 2 over 2, and sine of t equals negative root 2 over 2. And if we solve these on the unit circle, we know sine is equal to root 2 over 2. 2 different places at pi over 4, 3 pi over 4. And then we know that sine is equal to negative root 2 over 2 in the third and the fourth quadrant at 5 pi over 4 and 7 pi over 4. And there are our answers. So we end up with pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. So basically all the over 4 angles from the unit circle. All right, one more for us. So we have 2 cosine squared alpha plus 5 cosine alpha minus 3 equals 0. How do you suppose we're going to start? Well, if you guessed, say u equals cosine of alpha, you're exactly correct. So then we can rewrite this as 2u squared plus 5u minus 3 equals 0. This again is similar to one from the previous sets of slides where we had 2x squared plus 5x minus 3 equals 0. Now we solve that by using that AC method, where it factored to, in our case, it'd be 2u minus 1 times u plus 3 equals 0. If we solve each of those individually, we know we get u equals positive 1/2 and negative 3. And just like with the other ones, we're not trying to solve for u, we're trying to solve for alpha in this case. We know that u equals cosine of alpha. So we can set up two equations where we have cosine of alpha equals 1/2 and cosine of alpha equals negative 3. And when we solve these, we know cosine is equal to positive 1/2 in the first and the fourth quadrants. So that would be at pi over 3, 5 pi over 3. For cosine of alpha equals negative 3, well, that's not on the unit circle, so we'd plug it into our calculators and do inverse cosine of negative 3. But when you do that, you'll see that you get an error. And why is that? Well, note that what we have here, cosine of alpha, that's a basic cosine function. Remember that a basic cosine function oscillates between the values of positive 1 and negative 1, and negative 3 is well below that, right down here, right? So we know that there can't be a cosine of an angle equal to negative 3, so this one actually doesn't give us a solution. So alpha equals pi over 3 and 5 pi over 3 are our only answers. Whew. All right, wasn't that fun? Yeah, I know, it's great. Thank you for watching.